We can't taste the stars, and of course we can't smell the stars. We don't hear the stars, and with the exception of the heat of the sun, we can't really touch the stars. To understand the stars, we must use our eyes, our sense of sight, and instruments, a telescope like this, for example, to extend our eyes. Our eyes, after all, are sensitive to light, and light is what tells us about the universe. Atoms produce light, perhaps in a distant star they might be glowing. And the astronomer is able to collect that light, and by looking at it carefully, to understand what those atoms are doing. Well, it's really quite remarkable when you think about it. An astronomer painstakingly records and analyzes a tiny faint spot of light, working into the wee hours of the morning. And then that information allows the astronomer to understand, to deduce, really, the basic properties of a star, what it is, and then even to use that information to find out how the stars are born, how they evolve, and how they die. The stars and the galaxies are far beyond our reach, but light allows us to become better acquainted with them. Becoming better acquainted with light itself, however, is a much more difficult thing. We know what light is when we see it, but it's really hard to visualize what light truly is. In our everyday experience, we encounter light through its effects on the things around us. It's like gravity and electricity in that respect. We do understand it in those terms of how things around us are affected by it. We can describe it, and we can also predict its behavior. Well, we do know what light is. It's energy. It's radiant energy. And we can make these predictions about it. We can describe it precisely. And it really is important that we do so. Without light, we would know nothing of the universe, and with it, we're enlightened.
Light is the natural phenomenon that stimulates the remarkable mechanism of the human eye and allows us to perceive the infinite visual variety which the world and the universe have to offer. Although we don't understand the nature of light completely, we can explain some of the properties of light and how it behaves. Sometimes, light behaves like a stream of particles. And sometimes, it acts like a wave, like the ripples on a pool of water. By drawing a special shape called an ellipse, we can visualize how light behaves. Beams of light will converge at one point of the ellipse, called the focal point. Actually, every ellipse has two focal points. In this scene, the string is looped around the two focal points. By preparing a reflecting surface in the shape of an ellipse, we find that light from one focus will always bounce off the wall of the ellipse and pass through the second focus. Similarly, the ripples, or waves, will also converge at the second focal point. But would particles behave in the same way? If we produced an elliptical billiard table, we'd find that anyone could be a champion billiard player. Because no matter where the ball is hit, it'll drop into the hole. So, although it's not an either-or relationship, light seems to behave in a sense like a particle and like a wave.
I think the real history of light scientifically begins at the time of Newton. And at that time, there were essentially just two theories, and there have since remained just two theories in conflict. The idea of light as a stream of particles, and the idea of light as waves. Newton came down very strongly for the theory of particles, and Newton, as you can well imagine, had such authority that the corpuscular theory of light dominated all the way through the 18th century into the beginning of the 19th century, when the experimental facts indicating that light certainly did have a wave character could no longer be ignored, and the reaction was such that the wave theory entirely swept the board. Rather remarkably, however, the particle theory of light has been revived in the 20th century in the so-called quantum theory, the idea that light does consist of particles. But the end of this story is a rather remarkable one, as in most such black and white dichotomies, either this or that, the correct answer is both. In other words, the present theory of light says, yes, light has a particle aspect. Under some circumstances, it has a wave aspect under others. The real nature of light is something that transcends either of these rather extreme concepts.
We've also known for centuries that light will bend or refract when it passes from one medium to another, such as from air to water. The refraction of light can be illustrated with miniature cars and a model ramp. Obviously, the cars race down the hill in a straight line. But if a soft carpet is placed in the path of the cars to represent another medium, the cars are momentarily bent off course as they hit the slower medium. As soon as they leave the carpet and speed up, they resume their original direction. And that's essentially what happens when light is refracted. When it moves from air to water, the light slows down and bends. And when it moves from water to air, the light speeds up and is bent back to its original direction. Light can also be refracted by a transparent solid material. And that's essentially how a lens works. By replacing the flat wedge with a lens, the light can be focused. And by bending the light even more, the focal point will move closer to the lens.
The principle of refraction is sometimes used in the design of telescopes. And in fact, this Griffith Observatory instrument is a refractor. It has a lens, therefore, way up at the top end of the tube. In fact, that lens then bends the light that passes through it so that the rays meet at a focus, 16 feet and 5 inches down here. Well, we also have an eyepiece then attached to the telescope, and that magnifies the image. This telescope also has another one mounted with it. This one's mounted in tandem, and it's a smaller instrument, about 9.5 inches in diameter. But together, these two devices look a lot like what people expect to see when they come here to look through a telescope. Actually, however, today, most of the modern research that is done isn't done with refractors and an instrument like this. It's done with large reflectors. They use mirrors instead of lenses. Well, a refracting telescope, like this one with its very long focal length, is a good telescope for measuring positions and angles of objects in the sky. It can do the job very accurately. It's also a good instrument for visual observations, because with the eyepiece down at this end, you simply look through the telescope like this. A reflecting telescope, on the other hand, is a simpler telescope to design, and as a result, we can make them much larger. And we use them then to collect and to photograph the light from extremely faint and diffuse objects. But whatever kind of telescope we use, each has its own advantages. And all telescopes, of course, allow us to extend our eyes by gathering that little bit more of very faint white light that falls down upon us, shining from those distant stars.
We usually think of the visible light from the sun or from an artificial light source as being white. But what we perceive as white light is actually a mixture of distinct colors. And for centuries, we've known that white light can be separated into the different hues of the color spectrum, from red to violet, by passing it through a glass prism. Before the time of Sir Isaac Newton, it was believed that the prism itself produced the various colors. But in a classic experiment, Newton produced a color spectrum by passing daylight through a prism, then recombined the various colors by reflecting each color onto a single point. And, once again, the resulting spot of light was obviously white. This proved that the prism had not produced the various colors, and that they were simply the component parts of what we perceive of white light. Since visible light is a form of energy, it's logical to assume that the various component colors represent different levels of energy. For instance, red has the lowest energy level of all the colors in the visible spectrum. Orange has a slightly higher level of energy. Yellow is more energetic than orange, and green is more energetic than yellow. Blue is more energetic still, and violet is the most energetic form of visible light. So the various components of white light, the colors of the spectrum, are really just radiations at varying levels of energy. But what about the other types of radiation that are either more or less energetic than visible light? Normally, we're not as familiar with the other types of radiation, such as infrared and ultraviolet, because they're not visible to the eye. Although visible light is a very important element of our environment, it's actually only a small fraction of the total spectrum of electromagnetic radiation in the universe. Like visible light, the other types of electromagnetic radiation also travel in waves and can be characterized and organized by wavelength. Using ocean waves as an analogy, wavelength is simply the distance between successive waves measured from one crest to the next. And if we define wavelength as the distance between successive waves, then frequency is simply a measure of how many wave crests will pass a fixed point every second, or more accurately, the number of cycles per second. Obviously, the longer the wavelength, the fewer the number of waves passing a fixed point will be. So the lower the frequency for that particular type of radiation will be, providing the speed at which the wave is traveling remains constant. And each type of electromagnetic radiation, from radio waves to gamma rays, has a characteristic wavelength and a characteristic frequency. For any type of wave, whether it's electromagnetic radiation or even the waves in the ocean, wavelength, frequency, and the speed at which the wave is traveling are all related. The wavelength times the frequency equals the speed at which the wave is traveling. At one end of the spectrum, the radiation with the longest wavelength, up to kilometers in length, are the radio waves. The other types of radiation at successively shorter wavelengths are, in order, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. To compare the wavelengths at opposite ends of the spectrum, while radio waves can range up to kilometers in length, gamma rays can be measured in billionths of a centimeter. Besides wavelength, another factor that distinguishes one type of electromagnetic radiation from another is the level of energy at each wavelength. Very simply, the longer the wavelength, the lower the level of energy for that type of radiation will be. Increasing the level of energy beyond that of visible violet light produces ultraviolet radiation. Not only do ultraviolet waves tan our skin, but too much ultraviolet radiation can cause skin cancer. Increasing the level of energy beyond the ultraviolet produces X-rays, and this is one type of electromagnetic radiation which is proven to be invaluable in the field of medicine.
The reason for using X-rays in diagnosis of disease is that X-rays have the ability to penetrate the body and differentiate between soft tissue and bone and leave this image on the film. And the doctor can look at this image and see, for example, if a bone is broken or if there's a foreign body in some place within the film area, or in very specialized cases to look at blood vessels within the brain, within the heart, and things like of that nature. For example, in this film of the broken leg, we can see the bone because it absorbs radiation more than the soft tissue behind it. And so we clearly see the break. In this film of the blood vessels of the skull, by filling the soft tissue, in this case the blood vessels, with a dye, we can then see the blood vessels over the bone behind it.
Increasing the energy level beyond X-rays produces the most energetic form of radiation known, gamma rays. Uncontrolled exposure to gamma rays is deadly, but fortunately, the upper atmosphere shields us from the gamma rays and X-rays that strike the Earth from space. If we decrease the level of energy below the least energetic visible light, red light, we find the infrared region of the spectrum. Very simply, infrared radiation provides us with heat from a wide range of natural and artificial sources. Even the human body emits a certain amount of infrared radiation. Microwave radiation is slightly less energetic than infrared, since microwaves can penetrate foods much more efficiently than infrared. A microwave oven can cook much faster than a conventional oven, which uses infrared radiation. At the lowest energy level of the spectrum are television and radio waves. Radio and TV waves are sent out by powerful transmitters, falling harmlessly all around us, to be picked up and converted into sound and pictures by radio and television receivers.
Well, to describe what electromagnetic radiation is, I think one has to say that it's essentially the generalization of what we are all familiar with as light. Light, as customarily thought of, is a rather special thing only because of its physiological definition in terms of the capability of the human eye. But what light is, in covering a rather narrow range of the spectrum, is, in general, electromagnetic radiation, and that light is an electromagnetic phenomena, except the subject of electromagnetic radiation covers the whole range of the spectrum from the very longest radio waves down through infrared and the visible radiation and ultraviolet radiation and X-rays and gamma rays and so on and on, up in energy, down in wavelength. So it's the totality of phenomena whereby electromagnetic disturbances, shall we say, propagate at the speed of light.
Up to now, we've examined how the various types of electromagnetic radiation can be produced, detected, and put to use on the Earth. But the astronomer is much more interested in electromagnetic radiation from astronomical sources, raining down on the Earth from celestial bodies as close as the nearest planet, and as far away as a distant galaxy, perhaps billions of light years away. At the shortest wavelengths, most of the high-energy radiation, ultraviolet, X-rays, and gamma rays, is filtered out and blocked by the upper levels of the atmosphere, high above the Earth's surface. But a narrow window in the atmosphere allows visible light waves and a small amount of infrared radiation to reach the Earth's surface. Radio waves pass through a very broad window in the atmosphere and can easily reach the surface of the Earth. But where do the various types of electromagnetic radiation originate in space? Radio waves are emitted by some of the planets in our own solar system, especially by Jupiter. Also by distant nebulae and galaxies. Around the world, enormous radio telescopes collect radio emissions from objects throughout the universe, often at distances far beyond the range of the largest optical telescope. By studying the invisible radio signals from these distant objects, and sometimes submitting them to computer processing, astronomers can derive an incredible amount of information about a celestial body that may be billions of light years away. Infrared radiation is also emitted by the other planets in the solar system, the sun, the moon, and certain stars that are at a relatively cool temperature. Although a limited amount of infrared radiation reaches the Earth's surface, astronomers can make infrared observations with ground-based optical telescopes equipped with specialized IR detectors. And of course, the visible light waves that reach us from the sun, the planets, and the stars have been the object of astronomers' investigation for centuries. Today, astronomers record visible light from throughout the universe with enormous optical telescopes around the world. Telescopes that have the light-gathering ability of 1 million human eyes. The 4-meter Mayo telescope at the Kitt Peak National Observatory in Arizona. And its 4-meter twin at the Cerro Tololo Observatory in Chile. But since the radiation at the shorter, higher energy wavelengths, such as ultraviolet emissions from very hot stars, X-rays from clusters of stars, distant nebulae, and black holes, and gamma rays from exploded stars are almost entirely absorbed by the atmosphere, astronomers can only study these wavelengths by sending sensitive detectors above the Earth's atmosphere, carried by rockets, in unmanned astronomical observatories and in manned laboratories. In all, an understanding and analysis of the electromagnetic radiations from throughout the universe has become a critical and indispensable tool of modern astronomy.
For a long time, astronomers observed only at optical wavelengths, only in visible light. But about the time of World War II, we began to develop radar, and in the process, radio astronomy got going. We had the techniques developed to detect feeble radio waves coming from space. And for the first time, we're able to observe the universe in the light of radio waves as well as visible light. It really went a little bit earlier. Karl Jansky in the 30s actually was the first person to detect extraterrestrial radio waves, but radio astronomy really got its start after World War II. It wasn't until the space age, in the late 1950s, that we were able to send rockets and satellites above the atmosphere of the Earth, which protects us from X-rays and gamma rays and most ultraviolet radiation and parts of the infrared. Those satellites and space probes carrying detectors above the atmosphere were able to observe the entire electromagnetic spectrum. And that, of course, is a very recent addition to the astronomy of observing the universe. Visible light, centuries, millennia old. Radio waves, a few decades. The rest of the electromagnetic spectrum, only in the last decade or so.
Long before the invention of the telescope, at least since the time of the ancient Greeks, in fact, people have speculated about the nature of light. In fact, one of the earliest of the ideas was that light was a little particle or a stream of particles. But by the 17th century, light was most often described of as a wave. But also, Sir Isaac Newton, with his corpuscular theory, re-energized the old idea of light being a particle. Newton's ideas fell into disfavor, however, by 1801, when Thomas Young, the English physicist, performed his double-slit experiment. And with that, he was able to show that a couple of beams of light interfere with each other and produce a pattern of light and darkness that can be best explained by thinking of light as a wave. Well, today, the old idea of the corpuscles of light, as Newton called them, has actually been reincarnated through the quantum theory of light. But really, the quantum theory is far more involved, complex, and really precise than Newton would have ever imagined. And the whole idea of light being a wave or a particle isn't really a sensible argument anymore. In fact, light has properties of both. It might be best, in fact, to call light a wavicle.
The quantum nature of light is, in a sense, not unique to light at all. All atomic objects obey the laws of quantum mechanics. All atomic objects, to some extent, are akin to light in that they are not only particles, but they are also waves. This is not a theoretical concept, it's a perfectly experimental one. In fact, very early in the development of the ideas of the quantum nature of matter, the same kind of diffraction experiments that vindicated the wave theory of light were also done for electrons. You could observe the interference patterns, the up and down modulations that show the wave explicitly for electrons, and also this has been done for other atomic particles, neutrons, protons, and so forth. There is no doubt that this particle-wave duality is a fundamental aspect of all of matter. It is an intrinsic part of what we now comprehend as the quantum nature, the special atomic nature of particles. So the quantum nature of light is the quantum nature of all matter. The only thing that is special about it is what characterizes light as distinguished from other particles, namely the invariable speed with which light travels. If you like, the distinction that in comparison with the electron, which can be slowed down and made to be at rest, which essentially is what electrons in ordinary matter are, moving very slowly, the photon, the particle of light, can never be slowed down. It is always traveling at the speed of light.
The total spectrum of electromagnetic radiation is a very valuable, if not indispensable, tool for the astronomer. We know the stars only by their light. And like the universe itself, our ability to interpret the message encoded in the electromagnetic spectrum continues to expand. By collecting the light from a distant star and splitting it into its component colors, astronomers can learn a staggering amount of information about an object that may be millions of light years away.
The color in the light of a distant star is mixed into a composite image at the retina of the eye. We can spread it out into an orderly array and study it. This is spectroscopy, and without it, the universe would be incomprehensible.
Light is the natural phenomenon that stimulates the remarkable mechanism of the human eye and allows us to perceive the infinite visual variety which the world and the universe have to offer. And perhaps the most pleasurable visual experience is the eye's ability to distinguish between the various colors of the spectrum, the endless variety of colors on the Earth, and from throughout the universe. We usually think of the visible light from the sun or from an artificial light source as being white. But what we perceive as white light is actually a mixture of this